So there was a question about why the Saminon-Kirchhoff model has been chosen to have this particular form. And it really is based upon the fact that it's very much like the linear elasticity strain energy function for isotropic materials, except that instead of the infinitesimal strain, we have this finite strain measure. Okay, so really the question is why this form for Saminon-Kirchhoff. Okay, it's just that now when you look at psi hat, remember we have this form 1/2 lambda right, trace E square plus 1/2 2 mu okay. So if you compare this with the strain energy for linear elasticity, with the infinitesimal strain, right, where the infinitesimal strain is denoted epsilon, and it is just 1/2 of the displacement gradient plus its own transpose. Okay, in that case, then what you will see is that psi, let's denote it as psi for linear elasticity, okay, Le for linear elasticity, as a function of epsilon has exactly the same form. Okay, and this is really the reason, because you take exactly the same form, just replace the infinitesimal strain with this nonlinear finite strain measure, and you're ready to go. It's hyperelastic. It is frame invariant because we've picked E, and everything works. The only trouble is that it's not a very good model for nonlinear materials. Okay, in a sense, there isn't enough nonlinearity in it. Okay. This is the reason. And also what follows is that if you compute the elasticity tangent, right, as the second derivative of psi hat with respect to E, right, it is the same as computing the tangent of psi Le with respect to epsilon. Okay, they're the same. Okay, which is the same elasticity tangent. So in a sense, it is just the convenience of going to this model from linear elasticity that explains this particular construction for it.